there is statistics as a course. I'm going to say that again. The law of large number, the central limit theorem, provide us a foundational, result, reason why we actually, doing statistics. Because the central limit theorem in particular, enable us to apply our models to data that are non-normal. Because when data, most of the time, when you collect data from bank or from industry or from environment and so on like that, we realize that they don't follow normal distribution. Of course, we have a way to know whether they follow normal distribution or not. We can draw the histogram. We can draw the stem and leaf plots. We have several ways to identify, whether they follow normal distribution or not. Because if they don't follow normal distribution, but with central limit theorem, okay, because the central limit theorem is actually going to tell you, the normality of a random variable, is actually guaranteed provided we are choosing a sufficiently large sample size. So when we choose a sufficiently large sample size, even if the data do not come from a normal distribution, the distribution converges to normal distribution. Okay, why? Why do we need to celebrate when the distribution is normal? Because normal simplify complex situation, because normal provide a foundational basis for statistical models. If you want to talk about regression analysis, has anybody heard about regression analysis? Okay, thank you so much. If you want to talk about regression analysis assume the method in regression analysis assume a normal distribution. If there's no normal distribution, the linear regression is going to fail. If there's no normal distribution, hypothesis testing involving mean will fail. If there's no normal distribution, the confidence interval about the mean is also going to fail. And that is the reason why you are here learning this course is about chapter 6 and 7 mostly. And that's why the final will focus on chapter 6 and 7. We want to start from where we left off before the Thanksgiving break. Of course, I walk you through the law of large number. I walk you through the central limit theorem, and I'm going to say this once again. The difference between the law of large number and the central limit theorem. Go ahead.
So what happens if we mistake the strong law, the strong law with weak law?
Okay, what happens if we mistaken the strong law with weak law? That's a good question. Do you know what is realistic? Is the weak law. So what we normally emphasize, what we talk about a lot that we know is realistic in statistics is a weak law. So we don't normally talk about the strong law because there's no way we're going to mistake in that because the approach that we're using is probabilistic. And that is why the weak law is always going to take a center stage. Let me tell you this. You're always going to see us talking about what is the probability of the convergence of sample mean to population mean to be within a threshold. We normally have a threshold because the strong law doesn't have a threshold. The strong law is just trying to say, that converges absolutely to the population mean. I don't think that is realistic. But we're just trying to say this in theory. There are some things that exist in theory but may not be realistic. So if you're mistaking a strong law for... The probability of mistaking a strong law for weak law is very close to zero because in a stochastic environment, we normally, we have a probabilistic input. So, but you're going to see that hypothesis testing, confidence interval, all of that, they revolve around probabilistic convergence.
So when it comes to like Calc 2 stuff, it is all strong convergence. And when it comes to like piecewise function, we're talking about stochastic, right?
Yeah,
So
we're talking about stochastic, and in any statistical theory, there lies a probability theory. So we see that the convergence that make a whole lot of sense is probabilistic one, the weak one, because the strong one is too strict to achieve in a stochastic environment. Does that make sense? Okay, now, this is what happened. This is the bottom line. The law of large number, in general, law of large number, whether strong law or the weak law, enable us to realize that sample mean will converge to population mean when the sample size is large. I'm going to say that again. The two laws, the law of large number in general. Look at that, large number. It means, it's trying to say, your sample mean will converge to population mean if the sample size is large. Go ahead.
sorry for another.
No, you're free to ask a question.
The population mean is a parameter, so that means that there's a true one value, right?
Exactly.
That is not stochastic.
That is not stochastic. Not subject to variation. Yeah.
However, sample mean is stochastic. Right?
Sample mean is stochastic because it's subject to variation.
Is that the reason why you're saying that it does not matter which one, with large number?
Exactly. It doesn't matter because our intention is, you've asked a very good question. This is what happened. I want to know the average annual household income in United States. That's what I want to know. Now, I believe it exists. I believe it is fixed. It's not subject to variation. The true value of that. But this is the issue I got. If I want to get that exactly, then I need to study everybody in the United States, everyone that has income. That is not easy to do. And that's why in research, we are limited by budget. And what do we normally do is to take a sample. Instead of me to have a complete enumeration, I'm actually going to have a partial one. But, let me tell you this. When I investigate few people, and I get, what I'm going to get from the field is sample mean. But what do I need? I need a population mean that I'm supposed to have gotten from everybody. But we now have a belief here that the more sample that I take, the more the sample mean will be very close to the population mean that I needed in the first place. Does that make sense now? So sample mean approaching the population mean value when we are increasing the sample size. Why is increasing sample size not so easy? Because if I increase my sample size, then I'm going to commit more resources. Don't forget, I told you, we are limited by budget. But how are we going to do it? We still want to get efficiency. We want to get efficiency, and efficiency can be achieved, when you have a reduced variance. And that is why we now say what is going to happen in this case is when the sample size is extremely large, okay, the variance is going to be small. When the variance becomes small, then the sample mean will have a tendency to converge to population mean. That is the whole story. That's what the story is about. Now, the law of large number doesn't focus on the distribution. The law of large number only say when sample size increases, sample mean converges to population mean. But you know what? In statistical analysis, we actually we use a method that assumes normality most of the time, But what if in a situation where the distribution of a sample mean does not follow normal distribution? Of course, I walked you through this the other time using a sampling distribution technique where I go into a population and I take several sample size. I remember I gave you an example in this class when I asked you to go into the University of Minnesota population, take a sample size of 50, okay, and you are working on the same goal. Maybe you want to estimate the mean the average, maybe amounts spent weekly on food, okay, you actually going to have different means. If I ask 1,000 students to do that, then we have 1,000 means. Now, that is a justification that sample mean varies. Now, if I have a different sample means, I can plot the histogram to be able to see. When I plot the histogram, it may look like this guy, skewed. And when it is skewed, I show you on the lecture that I had on the Zoom the other time that when sample size is increasing, the population of the sample mean will converges to normal. We actually is going to converge to a normal. Okay, so that is central limit theorem. The central limit theorem is trying to say when the sample size increases, the distribution of the sample mean converges to normal. But the law of large number is not talking about distribution. The law of large number only focusing on sample mean converges to population mean when sample size increases. What is the step-by-step of the implementation of this in business? A particular business really want to know in this very company, what is the average amount we realize from sales? Because the value realized on sales varies day by day. Does that make sense? Now, what if a business really want to know? Because if a business want to know, the very first thing is we need to define a problem. What problem do you want to solve? Oh, I actually want to know the average amount that we realize in this company. Okay? Now the next thing is we will have the business to take a sample size. Okay? Now they take a sample size. Okay, you collect your data. Determine the sample size will mean, okay, I want to collect data. A researcher normally know ahead of time what will be the sample size that I'm actually going to choose. Of course, you now know in this class why you need to take a sample size at least story to guarantee normality. We have to take at least story. We don't just choose sample size arbitrarily. We need to be statistically guided. Now, they calculate the sample mean from the sample size. Then you repeat sampling. You know why the idea of repeating sampling is taking place? Because that is synonymous with if I ask 1,000 investigators to do the same, then we have 1,000 different means. So they have to, because when you take a sample and you find a mean, you can't rely on that value. It's just a single value. It could be wrong or right. It could be low or high. And that is why we call it's a random variable. And that's why you need a repeated sample. Now you calculate the mean of the means. There are several means, right? There are several means that I need to find what is the mean of the mean. Let me tell you this. The mean, if the sample size is large, the mean of the means will converge to the true value of the mean you were looking for. I'm going to say that again. The mean of the mean become the population mean. That is if this sample size is sufficiently large. Okay? So I just wanted to take note of that. Now we can determine the standard deviation of the means. Do you know that the standard deviation of the means is very, very essential in statistical world? The standard deviation of the mean is what we call standard error. We use standard error when you want to construct hypothesis testing. We use standard error when you want to construct a confidence interval. Without standard error, there's no moving forward. The standard error is the standard deviation of the means. The standard error gives us how means varies from the true values of the mean. That's all. So that you can see that. Then from there you apply the CLT. Now I want to walk you through an example now. Okay, you're going to see something similar in the final exam. You know what we want to do now? We actually want to benefit from the normality of the sample mean. We want to answer statistical inference. Go ahead.
You said the standard error is the standard deviation of the true value of the mean?
No. Standard error is the standard deviation of sample means. And you know what that measure? Look at me, how sample means, how they vary from the true population mean. I'm going to say that again. How many sample means do we have, depending on the number of investigators? If I have 1,000 investigators, I have 1,000 sample means. The sample means varies. From where? They vary, how they vary from the true mean, the population mean. That is what we call the standard error. But what about standard deviation of individual one? The standard deviation of individual variable, you know what that is telling us? The standard deviation of individual is telling us how individual value vary from the population mean. That is different from standard error. The standard error tells us how sample means vary from the population mean. Can you see the difference between the two now? Now, please pay attention to this. We want to capitalize on the normality of sample mean. When sample mean follow normal distribution, let me tell you this. It enables us to conduct statistical inference. When I say statistical inference, we can test hypotheses about mean. We can construct confidence interval about mean. We can do regression analysis. We can do analysis of variance. We can do all those tests in statistics that require parametric absorption. Now I need you to pay attention to this question. Achievement score of all high school seniors in a state have a mean 60 and a variance 64. Please pay attention when you see that. They're talking about all high school students in a state. Then that very mean that they give right now is a population mean. When they say population mean, you're talking about everybody. Okay? So 60 is a population mean. The variance, the population variance is 64. Does that make sense? Now, it said a random sample of n equal to 100 students from one large high school had a mean score of 58. Please pay attention. The 58 that we got here is a sample mean because they compute that 58 from a random sample of 100 students taken from a particular high school. Does that make sense? Now, is there evidence to suggest that this high school is inferior? Now, you know what we want to do right now? We want to compare the performance of a particular high school to all high schools in a state. Please pay attention. Okay? Now, calculate the probability that the sample mean is at most 58 when n equal to 100. Let me tell you this. Do you know that what we want to do here, please pay attention. Do you know that what this guy is talking about, probabilistically it means you want to find the probability that the sample mean is at most 58 when you choose a sample of individual, 100 individual. That's what you want to figure out. Now, you know what you want to do now? You want to conduct a statistical inference on a sample mean. Why are you conducting statistical inference on a sample mean? Because sample mean is believed here to follow normal distribution. How am I going to know whether it followed normal distribution or not? I will look at the board. They didn't tell me the distribution. Can somebody tell me why? I'm saying, Central limit theorem. Central limit theorem applied to what? What do you see? Exactly. What is large here? Sample size is 100. And what is the threshold as given by central limit theorem? Everybody? 30? Exactly. Even though they did not mention to me the distribution is normal or not, but I can judge from the sample size. When sample size is at least 30, then it's the distribution of sample mean is going to follow normal. It is only when the distribution of the sample mean follow normal that we can use a normal approach. Otherwise, if you use a normal approach, when sample mean does not follow normal, you actually going to mislead. Now, Now, let's see how it's going to be done. Please pay attention. Please pay attention. Now, we have two types of z-score. We have z-score for individual. We have z-score for mean. Now, take a look at this. If y follow normal with this as a parameter, the z-score is going to be y minus mu over sigma, right? But if this is individual, okay? That's individual. If I now want to talk about, I'm not talking about individual anymore. I'm talking about average. Y bar, average, follow, normal. I'm still going to have the same population mean, but the variance will be this. Please pay attention. The mean is the same. The population mean is the same for individual one and the sample mean, but the variance not the same. The variance for individual one, so it doesn't look I'm putting a bar. It's not a bar. Okay? For individual one is sigma squared, but for the sample one is sigma squared over n. Now here, the z-score is going to be y bar minus mu divided by square root of sigma squared over n. Look at the difference between the two. Now, actually, want to find, you've been told you know your sigma because they gave you sigma squared to be 64. Now, you want to find the probability of a y bar less or equal to 58. Okay, now you're actually going to use the group one. Can you see the group one? Okay, what is the square root of sigma squared? That will be sigma. Sigma divided by root n. Can you see that square root of n? Then I'm just going to plug in. I'm going to plug in, and I can apply normal. The reason why I can apply normal because n is large, n is 100. Okay, when n is at least 30, I can actually apply normal. Okay, now all what I'm just going to do right now to plug in my value, take a look at that, to check it, to make use of the table, done. Is there any question here? I'm done. Now, the probability is this. Then I'm going to tell you how to interpret this. Before, of course, look at this computation. Go ahead.
Are we just assuming that the standard deviation, or I guess the variance for this school is 64? Because like it wasn't stated that, it was stated that the mean is 58, but it didn't say anything about the variance.
Okay. It says something about both. There are three things here. Population mean, population variance, sample mean. Now, let me walk you back. Can you look at it? Achievement test score for all high school senior in the state have a mean of 60. 60 is population mean. And a variance of 64. 64 is population variance. Now, if sigma square is 64, what is sigma? That would be 8. So you've been given. So they're always going to give you that. They have to give you the population mean and the population variance. And the question they're going to ask will be based on sample mean. You know, here we have a sample mean of 58, right? Okay, we want to find the probability that we want to find is it has to do with the sample mean. I cannot find the probability associated with the sample mean without me having information about population mean and population variance. Have I answered your question?
Yes.
Okay. Now, you see what we got? Go ahead.
What is the reason why you call it individual and not population for the first one?
This one is just a particular high school student. This student, high school student, that is why. The score that this guy has in that subject, the score that the other high school, do you understand now? That is individual. But the second one, the average, is talking about the average score of a particular school, where there are so many schools involved in the state. You know, there are going to be so many schools involved. The average for this school, the average for the other school, the average for this school, the average for that school, the average is not going to be the same for all schools. If average are not the same for all schools, then the average becomes a random variable. Does that make sense? So this is why, so this is the one we use now. This is what we're going to be using. Because we're focusing on what? On the sample mean. As a random variable, we're no longer focusing on individual. Does that make sense? Now, we have a probability of 0.0062. This probability is too small. What is the interpretation? Take a look at it. Because this probability is so small, it is unlikely. Let me tell you this. When probability is small, we normally say unlikely. If it is very high, means when it is close to 1, it is likely. Now, it is unlikely that a sample mean from the school of interest can be regarded as a random sample from a population with that. Okay, it's like that very school, I don't know what is happening. Now, the evidence suggests that the average score for this high school is lower because you are comparing the average from that school with the state average. What is the state average here? The state average is the population mean. Does that make sense? The state average is the population mean. Okay? But that school average now is too small. Well, how do I know it's too small? Because the probability here, so it's actually going to look as if that particular school average is not from that population or it's not from the population, the high school in or high school in the states in general. Okay, so that's what it means. Take a look at that. The evidence suggests that the average score for this high school is lower than the overall average in the states. Does that make sense? Now we're making judgment. This is statistical inference. Now our decision is based on probability. Can you see that? Now, do you know another thing I'm seeing here? Pay attention. Pay attention. What is the convergence? The convergence, you are trying to say, the convergence between the sample mean and the population mean here, the probability of that convergence is what? The probability of that convergence is what? It's small. Convergence doesn't take place. That school average does not converge to the national average. It's very far from that. And that is why we normally talk about probability convergence. How is your convergence going to be strong when your probability of convergence is high? When your probability of convergence is small, then the convergence may not likely take place. Does that make sense? That's what we mean. Now, I want to go into another example now. Please pay attention. The service times for customers coming through a checkout counter in a retail store are independent random variables with a mean of 1.5 minutes and a variance of 1. They've given you what the mean is. They've given you what the variance is. Approximate the probability that 100 customers can be served in less than 2 hours of total service time. You want to figure out that probability, how? Please pay attention. Now, we're told that in this population, or any individual, Y1 up to Y100, don't forget we have 100 customers, come from a distribution. They did not mention that. They didn't tell us what the distribution is, okay? But all what we know is that the distribution has a mean of 1.5 and a variance of 1. But you know what we want to find? We want to find, this is interpretation now. Please pay attention. Look at here. It said, approximate the probability that 100 customers can be served in less than 2 hours. Less than 2 hours. Let's convert hours to minutes. That would be 120, right? 2 hours is 120, right? Then it means I want to find the probability that sum of y will be less or equal to 120. How do I convert this to mean? I want to convert this to average. What am I going to do? Divide this guy by hand by 100. Also divide this by 100. What do you have now? Now you're working with average. You're working with average. Can you see now? You're not working with average. Can you see what happened? We're not working with average. So the average, what is the probability that the mean is less or equal to 1.2? Okay, it's the same thing as what is the probability that the sum of y will be less or equal to 120? You're dividing, when you divide a total by the sample size, that's what you're going to have. Now that we have that, we can now go to standardization, can make use of the z-score. Take a look at that. Now, please pay attention. What is the variance? That is the variance of y bar. You remember? What this guy is saying, the variance, what this guy is saying is that the variance of y bar is sigma squared over n. Okay? That's what it means. And the expected value of y bar is mu. So here, what is the variance of y given in the question? Go back. What is the variance of y given in the question? They gave you 1, right? Look at the question. The variance is 1. Can you see? They gave you mean to be 1.5. Variance to be 1. Then plug in. That was why you have 1 here. Over 100. The sample size. Can you see that? Okay? And if the variance of y bar is 1 over 100, what is the standard error? The square root of that. The square root of that. Now, this is your z-score. Okay? Now, this is what you're finding. Y bar minus 1.5. Where is 1.5 coming from? That is the mean they gave you. Divided by that, at the end of the day, you're getting this result. Take a look at that. What happened to the probability here? The probability that you got, you're checking from table here. The probability is very small. What is your interpretation? The probability that 100 customers can be served in less than 2 hours is approximately that. When the probability is small, then you are not likely going to serve those numbers in 2 hours. That's what it means. Okay? This small probability indicates that it is virtually impossible to serve 100 customers in only 2 hours. Done! This final is going to be so easy. But if you pay attention now, I've seen a lot of final exam questions today. Here. So easy. Okay? Take a look at that. We're done. Done with that. Done with that. Is there any question here? When you have your probability value figured out, you need to make an interpretation for full credit. You have to interpret your probability. Now we're interpreting probability now. The probability based on sample mean. And we're using the idea of the fact that central limit theorem actually take a center stage. What if in a situation where I ask this question and maybe the sample size was 20 or sample size less than 30, we cannot we can apply the use of a z-score. Normality, central limit theorem gave us condition for normality. Normality facilitates standardization. Standardization facilitates the use of z-score. When you make use of z-score, then you have a simplicity of probabilistic computation. Look at that. That's how easy as that. Now, I'm moving. Now, we'll be focusing on a single population. What if in a situation where I want to focus on 2 different populations, where I want to talk about the difference of means? Take a look at this. Suppose that X1, but before going into that, let me do this. If I have 2 different means, let me tell you this. If this guy, let me be using Y. If this guy is a random variable, and this guy is also a random variable, the difference between them is also going to be a random variable. Oh, this is the average from school A. This is the average from school B. But you know what we want to do? Is there a statistical significant difference between the 2 schools with regard to performance in math? If we want to do this, we need the distribution for this guy. The distribution for this guy, we're actually going to follow normal, mu1 minus mu2. But you know what the variance is going to be? The variance is going to be this guy. Can you see that? So in a situation, so what I'm trying to say, the mean is this. Okay? The variance is actually this. Can you see that? Can somebody tell me why is it that there's no covariance here? Why is it that there's no covariance? Eh? Because they are independent. That's it. Okay? Now, the standard error now is going to be the square roots of this guy. I know you've seen this before in hypothesis testing or stuff like that. Now, let's take a look at it. Suppose that x1, x2 up to xn, and y1, y2 up to yn, what are they saying? Oh, s1, s2 up to sn. Student score in this class, from maybe I have m students in this class. In the other school, I have n students. That's why you see, and they are independent random variable. Okay, with your variable si normally distributed with the mean, mu1, and sigma 1 squared, and the y1 normally distributed. Now, let me tell you this. In this question, they've already told you the population is normal. Whether the sample size is small or the sample size is large, okay, the random variable here, the difference of the sample mean will follow normal because you've been told from day one that it is normal. Does that make sense? Now, the difference between the sample mean is then a linear combination of n plus n, normal distributed random variable. Okay, now the question now, find the variance of that. Suppose that sigma 1 squared equal to 2, sigma 2 squared equal to that, m equal to n. The two schools have the same number of students. Find the sample size so that x bar minus y bar will be within 1 unit. Can you see that? Within 1 unit, that's a threshold, right? Within 1 unit, if difference exists, okay, within a unit, 1 unit with a probability of 0.95. How are we going to solve this? The first one is talking about the mean, because if I want to make an inference about the difference of mean, I need to know the mean of the difference. I need to know the standard error as well. Let's start with the mean. Please pay attention. You know what we want to find? If you take a look at this, it said, if you take a look at this, it said, find the sample sizes so that x bar minus y bar will be within 1 unit of this. 1 unit of that. This is the true mean, right? This is the true difference of means. This is on average, we said on average, expected value of the difference between the two sample mean converges to that. Now, please pay attention. Probabilistically, this is the interpretation. I want to find the probability of the absolute difference between the difference of the sample mean, okay, converging to the population mean within 1. That 1 is what? The threshold that I talked about the other time. I told you the other time, the probabilistic inference that we normally conduct rely on the weak law of large number, not on the strong law. The strong law, not realistic. Okay, now it's going to be 0.95. You've been given that. How do I remove an absolute value? Mathematically, if I want to remove an absolute value, I'm actually going to say, because I have a 1 there, it's going to be -1 and 1 to remove the absolute value, mathematically. Then what am I going to do now? What I'm actually going to do is I want to find a z-score. Some of you may be wondering, why is a z-score not friendly? Why is z-score like that? Please pay attention. The first one, what do you see here? -1, right? The z-score for that will be -1 minus mu1 minus mu2. Mu1 minus mu2 under hypothesis assuming to be the same. Okay? That's why you see a -1 here on the top. Also, you're going to see that here, 1 minus the difference of the Two population mean will be that. Now, divided by the square root, don't forget this guy. Sigma 1 squared N1 sigma 2 squared N2. What is sigma 1 squared, sigma 2 squared? I think they've given you the variance for each. What did they give you?
2 and 2.5.
Huh?
2 and 2.5.
2, okay, here, thank you. Do you see that? Sigma 1 squared, 2. Sigma 2 squared, 2.5. They've given you already. They plug them in. 2 and 2.5. You know, I can add this to this when this is the same. N1 and N2, we are told in the question, they're taking them as M and N. Can you see that? If they are the same, then I can just add that to that, and that will lead me to what I have here. And the moment I have this, don't forget, I'm actually want to find, I'm solving for N. So I continue to go like that all the way. Then I got my N to be that. Then I'm going to approximate that I to say at least 18. I need 18 students from each school, at least 18 students from each school to be able for this probability to hold, for this guy to hold, for the difference to be within 1, okay? So I need 18 students from each school, which is what you're seeing here. Can you see that? Okay. Now we've been dealing with average, sample mean. We're also going to have a question that has to do with proportions. Let's pay attention. A pollster believes that 20% of the voters in a certain area favor a bond issue. If 64 voters are randomly sampled from a large number of voters in this area, approximate the probability that sample fraction of the voter favoring the bond issue will not differ from the true fraction by more than 0.6. Will not, okay? Now, you'll be, let's collect the data. The data here, 20% is P. N is, you can see that? N, 64. P is 0.2, okay? Now, how do we interpret? Take a look at what it says here. Please pay attention. Look at the question here. It said, the probability that the sample fraction of voters favoring the bond issue will not differ from the true fraction by more than, will not differ by more than. How are we going to interpret that? This is what we mean. And I'm going to explain that to you now. Please pay attention. Please pay attention. When we're talking about a voter stuff, that is Bernoulli. You remember what we did in Bernoulli? Bernoulli? You remember Bernoulli? If Y follow Bernoulli, what is the parameter? P. Right? In Bernoulli, what does it mean? What is the expected value of Y in Bernoulli? P, right? You remember? What is the variance of Y in Bernoulli? P into 1 minus P. Now, if I now want to talk about average in Bernoulli, if N is sufficiently large, the Bernoulli converges to normal, right? By central limit theorem. Any distribution will converge to normal by central limit theorem. Okay? Now, the Y bar, please pay attention. The Y bar, instead of Y now, the Y bar is actually, we're going to have the mean of that to be equal to P, the variance of that to be equal. Don't forget, we normally say sigma square over N. What is sigma square in Bernoulli? You know, this equal to sigma square, that will be P into 1 minus P divided by N. Please pay attention. So the variance is that. The variance of the mean in Bernoulli, when central limit theorem apply, is P over 1 minus that. Can you see that? What would be the standard error? The square root of that. That was why you're seeing this. That was why you're seeing this. Can you see that? Can you see that? Can you see that? And what about here? you know, the probability of the absolute value between y over n minus p. Of course, p here is the population mean for Bernoulli. Then y over n that you are seeing there is the average. Y is the total. A total divided by n, now it's y bar. That's what you see. So now, in interpreting this guy now, if you look at the question, you've already been given that, 0.06. All we're just going to do is the probability of the absolute difference between y over n and p. P is the mean. Whether here or here, the mean remains p. The true mean is p. Okay? Less or equal to 0.6. If I want to remove the absolute value, in mathematics, if I want to remove the absolute value, what is going to happen? Negative at this side, positive at that side. That's why you see, that's why, take a look at this guy here. That's why you're saying this. Now, I want to standardize this. I also want to standardize this. That is the standardization here. I'm only going to put this one here, divided by the standard error. Where is the standard error coming from? Take a look at this again. Bernoulli that we've done in this class, the mean is P. The variance is that. Now, if central limit theorem applies, if CAT applies, okay, that is, n is at least that, then the sample mean, the mean of the sample mean is still going to be P. The variance of the sample mean is sigma squared over n. What is sigma squared for Bernoulli? I'm going to put that divided by n. What would be the standard error now? The standard error now would be that. This is the one you're going to use in the standardization, which is what you are having here. At the end of the day, okay, you're gonna return to where you are checking table. There you go. That is the probability. Like I said again, I've seen a lot of exam questions here today. I'm actually going to be finishing our course for this semester on Friday. When is the last day of instruction? Next week, Wednesday, right? I'm finishing this Friday. But you know what we're going to do on Monday? Is final practice question. I'm actually going to release final questions tomorrow or Wednesday, final practice question. And that will focus on 6, 7. But you know what? Chapter 6 and 7, what we're doing now and what we're going to do this week, they are very, very crucial to the final. If I were you, start studying them. This is how far I can. Oh, that is even the end. Oh, okay, that's the end. But I think I've also uploaded the material for tomorrow. The material for Wednesday. You can check the canvas. Okay, stay safe. Bye for now, everyone.